kick my ass. So here's the average over here. The average continued. We have to take each data point and multiply it by its probability. So the first data point is 1.
With 1/6.
With a 1/6. Because each one is going to happen 1/6 at a time. Okay, each one's going to happen 1/6 at a time. Then we have to add to that the 2 and its 1/6. The 3 and its 1/6. And so forth. Let's pump this over a little bit further. So that's what it looks like arithmetically if you write the whole shebang out, yes? The whole shebang out. Now, what does each piece mean? That's kind of funny too. Like, what is this part of it? What is that? I mean, numerically it's 1/6. Yes, it's 1/6. But what is that actually telling us? If we carry each of these down, this is now 1/6. This is now 1/3, I think. 2/6. Yeah.
You have a higher chance of rolling a 2 than you do a 1.
Do you?
I don't know.
Let's go with that, Lauren. I love that comment. Thank you.
But that's what it looks like. If I'm looking at it.
Ah, good. Let's look at it differently. Let's look at it differently. Only because I love what you said. You said, look, it looks like you have a higher chance of rolling a 6 than rolling a 2. And it does look like that because you get bigger numbers on the right than you do on the left. But we already agreed you have the exact same chance of rolling a 6 as a 2, right? So what becomes higher the further right you get? Go ahead, say it. The number on the x column. So in other words, even though a 6 is just as likely as a 1, it's contributing 6 times as much to the average when it happens. Does that make sense? This is like when you take out a life insurance policy and you die, right? You get the big payout. You get the big payout. Well, somebody does, I should say, right? You know, right? Yes, but somebody does. Your beneficiary does. You just get the big payout. But when you live, you're on this end of it. You're getting the small payout. Otherwise, the negative payout, which is you paying your bill. Go ahead, Natasha, go.
The number of pips why are we putting a numerical value on it? Wouldn't it be like, what if there are pictures on it?
Good. Here's the question. What if the pips weren't actually numbers, but instead pictures? Then this is all out the window.
Yeah,
you can't average pictures. It's qualitative data, right?
Yeah.
Unless
Let's
you
say
assign pictures a number.
No, this isn't good. Good. That's still qualitative data, right? That's still qualitative data. No, hang on. Natasha's got a good point. Who the heck? The fist fight is starting. This is great. The fist fight is starting. I love this. Who says that can't be 2? That can't be 4. That can't be -12. That can't be 262.13. Nobody says it. It's just these ones that you guys have in front of you say 1 through 6. I'm not saying that that's right or wrong. I'm just saying it is.
The math
Is that fair?
Yeah.
You're asking a question that will be answered in spades on Tuesday, and I promise you that. But right now, it's just these random number generators have those particular numbers on them. Feel free to fist fight that. I love that. But that's the same question you gave last time. It's like, wait a minute, out. This seems arbitrary. In some ways, it is. But those are the values we've got. Is that fair?
Yeah.
Good. Great question. Other questions or other comments about that? That's fantastic. Thank you, sister. So, in other words, I heard a bunch of people go, oh, when I mentioned that. The 6 contributes more to the overall average than the 1 does. It contributes exactly the same amount, 1/6 at a time. But it contributes more towards the overall total. And what does this all add up to? It balances out to 3.5. It sums to 3.5. If you actually add all the math up, it's going to be 3.5.
So it's just weighted differently, like you were saying.
That's the whole point. Except the weights and the probabilities are the same, but the values you're averaging are different, much like the lollipops in the beginning of the term. I had 10 of you standing up here. Each of you had a 1 in 10 chance of me selecting once you're up here. But some of you had 7 lollipops, some of you had none. But once you spread it out, on average you have 3.5 according to this. Here's a question I have for you. What's the standard deviation around that average? Now, I do not want you calculating this by hand because it's a pain in the butt. So everybody, if you would, if you haven't already done so, enter your new probability distribution into L2. So you already have L1 ready to go, yes? You already got L1 ready to go. Enter in L2.
So we're going to delete our frequency.
You delete your frequencies. We're done with them. They served us well. We'll make new ones on Tuesday. Clear out L2, put 1/6 all the way down, rerun 1 bar stats. Very, very good. Very good. Thank you.
Go up the top of that.
Yes.
It clear and then it'll drop.
you guys?
We don't have one.
1/6 of each one?
There's no.
What the hell? I hate this class again. I love it, Lauren. It's fantastic.
Does this have an all?
Sure it can, and we're talking about why.